Okay, so hello everyone. Let's start the course. My name is Orçun Orhan. I am an avionics engineer at MGP program in TUSAŞ. So we will be having the course Introduction to Avionics with you today for like 2 hours. Normally we are giving this course at TUSAŞ Academy for like 3 days, but with you we will just try to cover like most of it in 2 hours. We will not go into too much details. It will be really an introductory level to the avionics systems. I mean, the purpose is just to give you the idea of what kind of equipments we are using and what is the purpose of using them in the aircraft. So the presentation content will be like, we will start what is the avionics, a little bit history of the avionics systems in the aircrafts, what is the importance of the avionics systems, why we are using them inside of the aircrafts. Then we will just move on with the architecture. What is an avionic architecture and why we are building those in our systems. Then we will just talk about the data bus systems, the systems that we are actually sending the information between the equipments inside of the aircraft. Then we will just move on with the subsystems, which will be the air data systems, display systems, navigation systems, communications, and autopilot systems. As I said, we will just be going through all of it, but in a really basic level, so we will not go into details of every kind of equipment. But if you have any questions, you're just free to just stop me and then ask your questions. So what is the avionics? It's actually a term that is a combination of two words, which is first one is the aviation, the other one is the electronics. And when they come up with the avionics first, which means that these are the electronic devices that is used in the aviation systems in the aircraft mostly, but it's not just the aircraft. It could be the satellites, rockets, every system in the air, in the aviation that you used, and all the electronic devices that you are using in those systems is called the avionic systems. But what is the responsibility of those systems? To ensure that the flight mission is performed safely and efficiently by the flight crew. A little bit history. So the first, as you already know, the Wright brothers is the first one who actually make a first successful flight with a heavier than an aircraft. It will be the first one in the history of humankind, which is kind of important for us because those improvements, the aviation systems actually start to grow up. Second part is the World War One. Why it is actually important for us because during the World War One, there weren't much avionic systems used inside of the aircraft first, but only the pilot is trying to navigate through their actual visual sights through the aircraft, and it will just try to move the aircraft. Why they are using the aircraft is just to get some information from the other lines, trying to understand what is the enemy is actually trying to doing, and then try to come back to their base and then give the information. And then maybe a close combat sections they were using, but there weren't any really much avionic equipment used in those aircrafts in that area. But the first important guy in the history kind of say that Lawrence Perry, because as we call this is the first autopilot flight. Why we are calling it as like the first autopilot flight is in I think is 1914 there was a air show in France in Paris, and Lawrence Perry with its aircraft there was a gyroscope in his system, and then the lever he connected mechanically to that gyroscope, and during that air show he flied with his aircraft but without any controlling the aircraft. The aircraft was just moving in a stabilized way and then getting its directions through its actually gyroscope. So in the history, this is called is like the first autopilot system. It's not, of course, like the autopilot system that we are using nowadays, but it is a system that is just controlled by a gyroscope, not by actually a human. So this is the reason they just called it as like the first autopilot flights in the history. The second important guy is just like the James Doolittle. He's an American guy. We called it as like the first blunt flight, but why it is actually important is he just only trusts its avionic systems inside of the aircraft. The right picture is actually showing you the aircraft he actually used during that blind flight, and then he didn't get any visual sights from the outside world. He only just get the information through his actually avionics. And it is the first time someone actually tried to fly an aircraft without any visuals from the outside world, with only just getting information from the avionics. He didn't look at the outside. He just get his like the altitude meter, speed meter, his gyroscope, and then with those information, he make a successful takeoff, a cruise flight, and then a landing. So this is kind of important in the history because it just showed that the avionic system is actually enough for an aircraft to fly by itself. There is no need to get a visual from outside world. So that was the importance of inside of the history. The World War II is kind of also a little bit important for the avionic system. Why is because during the World War II, most of the avionic systems started to be produced and then start to be engineered. One of them is the radar. We will also be talking about those inside of the course. And all of these avionic systems that we are seeing in the right side is actually start to be used in the World War II area in the history. So it was also kind of a little bit important date for the avionic part. Navigation systems like the one that you see in the left picture in the presentations also start to be used in the World War II area. So we will be also going a little bit details about those during the course. But most of the system, as I said, we are using nowadays is also started to be used in the World War II. So that is kind of an important era for the avionic systems. Fly-by-wire, why we are calling fly-by-wire is that important? Hi. Is there any question? No, I think. So it was a mistake. Okay. So I'm continuing then. So fly-by-wire is also important. Why? Because before the fly-by-wire systems, all the control surface controlling and everything in the aircraft and the aircraft systems is controlled by mechanically, not by any electronics during those areas. But when the fly-by-wire systems actually start to be used, like in 1987 in the Airbus and 1994 in the Boeing, so it was an area that the controlling systems just start to become like electronics, not like mechanically you start to control. You're just actually giving mechanical control inputs, but every surface and everything is just commanded by electronics. So it was also an important area because it's also been able to be just decrease the aircraft weight because we are just starting to use like electronics, not like mechanical parts, and then we are just decreasing all those mechanical parts from the aircraft and start to use most of the electronics inside of the aircraft. One of also the important part is like the GPS satellite navigation. Why it's important? Because before the GPS, we were always trying to get our navigation through the ground. And there are like beacons on the ground, and we were just trying to get our information through those beacons and trying to understand our location on the air. But with the GPS, we also start to get our locations, understand our locations through the satellites in the space. So it was also an important area for the navigation, and it just improved the location finding for the aircrafts more easily. In today's conditions, we can say that it's not possible to just have an aircraft to fly without all the avionics because we have like those fly-by-wire systems, all those motors and everything is just, we are using all them for like avionic systems. So if there is no avionic system inside of an aircraft, so it's not being able to be flight. So we can easily say that it's not possible for an aircraft to fly without an avionic systems in today's conditions. So we are just dividing the air vehicles into two categories. The first one is the lighter than air, and the second one is the heavier than air. The lighter than air is like the really small aircraft, but the heavier than air is like the aircraft that you're also trying to design by yourself. We can also just divide them into two sections, with motors and without the motors. Without the motors is like the gliders that we can say, but with the motors one is like the if we are using them in the inner atmosphere or the outer atmosphere will be of course the space, and the vehicles that we are actually building for the outer space will be the space shuttles or the rockets or the missiles. And for the inner atmosphere, we are just building like two different kind of aircrafts. The first one is the fixed wing ones, the other one is the rotary wings one. So it's the importance of the avionic systems. So there are like two main tasks that an avionic system is actually doing for our aircraft. First one is the successful execution of the aircraft mission, because every aircraft or every avionics system that you can say has like a mission to be built on. Because when you start to create an aircraft, there should be a mission. You are just not creating or building or designing an aircraft for just to fly. There should be a mission for it. And first task for the avionics system is to successful execution of that mission that the aircraft is just built on. And the other task will be the safety of the flight crew. Of course, if there is any crew inside of the aircraft. Nowadays, the UAVs that we are also designing, so there is no crew that is actually inside of the aircraft. But at that time, it will be the safety of the flight crew, but not the safety of the flight crew, but it will be the safety of the aircraft. As we already said, in today's conditions, aircraft cannot perform their missions only with the mechanical system. There should be some electronical systems inside of the aircraft that is actually also providing you some information about like air data, navigation, or any communication between the ground and everything. So there should be some electronic system inside of your aircraft to just fly the aircraft. So we have like ATA classification, which is the avionics system classification according to the Air Transport Association. So there's a numbering system, like some of them is just like for some systems specifically. For example, the ate22 is like the automatic flight control systems. ate23 is like the communication systems, and which are like there are some subsystems like the radios, locators, radio control panels. Or for example, the ata34 is like the navigation systems, which are the radio navigation, inertial navigation, landing and takeoff systems, or ADATA systems. So why we are doing this qualification? Because the aircrafts are really big, so you need to just like to classify some subparts, so that when you're actually designing, you need to be understand what parts you're designing, and then there should be a common sense. So this is the reason that we are using the Air Transport Association's classifications for our aircraft designs. Like these are again some of the classifications between the sub-classifications. So what is the control theory? In the basics, the control theory is that you're trying to build a controller to control a system. There should be a system that is designed before you. So as a controller, you need to like try to create a controller on that. What the controller is trying to do with a given input, it's just trying to get that system to a desired output. For that, there should be some sensory systems that can give some feedbacks. If there is any measured outputs with those sensors, and then it's giving it to the back to the reference, it means that this is a closed loop. If the system is just like an open loop, then there will be no sensory system. You will not be getting any feedback from your outputs. You will just directly give your input, and then the system with your controller trying to get that desired output. But if you try to get any output reference in your system, means that this is a closed loop. So it will be a much more, not easy, but it's easier for you to reach the desired output. And for our systems, what will be the controllers is actually trying to control will be the control parameters, which are the elevator angle, rudder angle, aileron angle, flap angle, and the thrust quantity. So with those, these are like the control surfaces and the motors. So with those informations and with those inputs, you will actually trying to control your aircraft in the air. So what is a cockpit is? Actually, cockpit is the section where the aircraft is actually controlled and managed. It could be in the ground for like UAVs, or it could be in the aircraft for like the fighter jets, or for like the other aircrafts. So, but this is the area where all these aircraft information is actually shown to the pilots. So through some feedback sensors, or between the screens, we are actually giving all those information to the pilots so that they will be able to fly the aircraft. Through history, there is actually a simple T organization that is used also in the really back times, but also in nowadays. We are just trying to follow the simple T organizations in those screens that we are actually giving information to the pilots. What is the simple T organization? There is like a T shape. All these information will be shown to the pilots. On the left side will be the airspeed indicator. On the right side, there will be an altitude indicator. In the middle, there will be a status indicator, and then the heading indicator. So all these four information is actually shown to the pilots with a T organization. And in also the old times that is shown like this, and also in our nowadays in MFTs, these information is actually shown like in the same way that is shown in the past. So on the left side, you're actually seeing an inside of an aircraft like in the old times. So it's like the T shape. On the left side, you have the airspeed. On the right side, you have the altimeter. Heading and the status indicators are in the middle. And on the right side, this is an MFT. So this is like the more modern way that you're using and showing information to the pilots. And if you just see that this is the same information. On the left side, there will be the airspeed. On the right side, there will be the altimeter. And on the middle, there will be the status indicator and the heading indicator. The same way, like the T shape that you are showing in the similar and the familiar way, information to the pilots. I mean, as we always said, all cockpit designs today, modern or classic, whatever you're actually designing, are the products of serious human factors engineering. Because what you're trying to do is just like they're trying to give information to the pilots, but in a way that it's not going to confuse the pilot. Because nowadays there are too many information that can be shown to the pilots. But if you're just showing too much information, and if you just show them in a way that it's just going to confuse the pilots, so you're actually creating a negative effect on the mission. So what you need to do is just try to give not less information, but the necessary information in a way that it's not going to confuse the pilots. So all these actually the cockpit parts is just designed in a considering a human factors engineering. And these are some of the standards, but we're not going to go into details about those. And let's start talking about avionic architecture. So what is an avionic architecture? You can think it as like, so you have already all these equipments. So for an aircraft, you already select as an avionic engineer, you already select all your equipments which will be used to fulfill your mission. But how you are going to connect all of them? I mean, which information is actually be going through to which equipment, from which equipment to which equipment, or how the power is actually going to those equipments. So how we are going to show them using an avionic architecture. So it is like a diagram showing the connections and the communications of all the avionic system in your aircraft. So this is why this is the first and the most important issue in the aircraft design for avionics, because without knowing the connection between the equipments, you cannot actually start building your aircraft, start also designing your aircraft, because some of your equipment is actually working with different voltage levels, so you need to be actually selecting proper equipments and then have the proper connection with those. Or some of the equipment is actually using different kind of protocols to communicate. So if you cannot actually select the right equipments to communicate with each other, you cannot actually again build your aircraft. So if you don't have a really proper avionic architecture with all these connections, you cannot design your aircraft. So the paths followed while creating the aircraft, as we always say, examination of the aircraft mission and the requirement set. So according to that, you need to determine whatever equipment you are going to use in the aircraft, and then selection of the suitable equipment that can fulfill the specified functions, and determination of the data paths between the selected equipments. So which equipment is actually going to give information to what, and how those equipments is going to get their power and from where. So this is like a small part of an avionic scheme of an aircraft. So over here, for example, with the red lines, you're actually showing the power lines. Or for example, with the blue ones, there's like the radio frequency, RF communication between those equipments. You're actually showing, for example, with the green one, you're actually showing that there's a communication between the equipments with like an ase401 protocol and then connection they have. So in that avionic architecture, when you're designing an aircraft, you're just showing how all these equipments are actually connected together. So today we are actually categorize all of our avionic architecture into three main headings. First one is like the central architectures. The second one is the federated architectures, and the third one is like the modular architectures. But there will be also another one, distributed architecture, which we are not using anymore in our aircraft, but this is like the old way that we were using. So what is like a distributed aircraft? So the most and the primitive and the simple type of the architecture that is used in the aircrafts. There is no connection and communication between the avionic systems. The only connection between the avionic system is like the human factor, which is the pilot. So all this system is just like separately showing information to the pilot, and the main processor in the aircraft is the pilot. So it's just processing all those information and then making a decision about what to do or how to control the aircraft, how to control the control surface or the motors, and then having the decision is just actually applying them through using some mechanical levering. So there is no connection between the systems. Any system is not actually giving any information to each other, only giving information to the pilot. So that's why we are just saying that it's distributed. So everything is just like distributed and then giving information separately to the pilot. So in this architecture, the main part is like the pilot. He's the main guy. So what we are saying that the central architecture, you can just think it as like in the distributed architecture, there was the processor was the pilot. So he was processing every information. In the central architecture, without the pilot, you're just eliminating the pilot and then putting a microprocessor in the middle. So every information from the systems is actually, avionic system is coming to that central microprocessor and is just processing every information and then giving some information to the pilots. Of course, there is again a pilot who's controlling the aircraft, giving necessary information, getting the necessary information to understand what to do with the aircraft. But without giving information, all the information to the pilots, first you're just centralizing every information into a one microprocessor, processing the information, and then showing to the pilots. What is the advantage is like the simple design, easy programmability, because there is only one microprocessor. You need to actually program to do what you want it to do. But what is the disadvantage? This is like the long bus connection. So what is the bus connection? Is like the data lines between the microprocessor that is in the middle and your subsystems, because there is only one microprocessor and all this system is actually connected to that microprocessor. So imagine that there is a system on the wings part or in the tail part, and your microprocessor is just like inside of your fuselage, and all this information needs to come to that part. So there are like some big bus connections. So if there is any failure in those bus connections, then they are actually losing control of the aircraft. Or low flexibility in software, because there is only one microprocessor you need to control and you need to program. So I mean, the flexibility in that software is kind of low for you. The increased sensitivity to change, because if you need to change one part, you need to also change it inside of your microprocessor. Maybe some of the systems actually working together, but maybe if you change one system, you need to change all the program that is working on inside of the microprocessor. And then what we came up is like the federated architecture. So over here, every subsystem has their own microprocessor processing every information they need and then sending it to a central computer. So what is the advantage of this one? Because you are not directly getting any raw information to the microprocessor, because in the central architecture, the microprocessor is trying to get all the raw information and then trying to get understandable information out of those. It's just trying to process all of it, all of the raw data. But over here, all the raw data is actually processed in the subsystem by itself, and then the necessary information is only sent through the central processor. So what is the advantage? Like the short and few data buses, because all these subsystems, there is a microprocessor. So every system is just connected, every subsystem's equipment is actually connected to that microprocessor. That one is actually processing and only sending the necessary information. So there is the data buses, like the connection between the subsystems and the main connector is much more less. And it is much more fast program operation, because if there is any failure in your subsystem, you don't need to change the main program. You need to only change and look at the subsystem's microprocessor program to understand the problem and the failure. And if you just fix it, you don't need to change the main program over here. As also, like you can say that this is much more easier for the bug detection. But what is the disadvantage? You are just increasing the processor intensity in your system. I mean, the processors are not cheap. So you are just putting much more processors in your system. So you're actually increasing the cost of your aircraft. So as we already said, the number of electronics equipment, like with the federal architecture, the processors actually, number of the processors increased inside of the aircraft, and the cost of the aircraft start to really increase. And then that was the reason they just come up with the modular architectures, designing an architecture with avionics modules instead of the avionics subsystem. So there is again a main processors, but inside of the main processors, there are like some modules that you can easily program, and this is adapted for like the subsystems. So you're not just dividing directly every system to their subs and then just makes them to process all the data. You're somehow collecting them, but then processing between these different types of processors in your system. You can just think it's like an IT department of your system. So there are like some modules. If there's a failure in the module, it will be easier to also debug, and then you can easily just change them. But of course, in nowadays architecture, there is not just like only modular architecture, no, just only federal architecture, but there's like the combinations. So in the aircraft, there is still like some modular architectures, federal architecture, and also some central architectures. There's just combined, all of them is used in the aircrafts. So data buses, we will just start talking about. So what is the data bus? Is like the name it's already tell, is like the channel that is used for the avionics systems to give information to each other, to communicate. It is like a nervous system, you can say. All the communication and the data transfer is carried out through these channels. So if there is any failure in the system, in the communication, so there is no actually information going through from one system to the other. So there should be also some like backup channels for every data bus, because if you only have like one data bus between one device to another, and there, if it is like the important data bus for your information, if there is any failure in that data bus, so there is no way to just give that information to the equipment that is needed. But if there should be a backup channel, so if there is any failure in the main channel, then you can also send your information through the backup channel. So there is always a necessity in the aircraft to just design with the backup channels, with like the backup equipments. So types of data bus is again like there are like two kinds. First one is like distributed data bus. Second one is like the centralized data bus. So what is distributed data bus? So every equipment is actually connected through not one cable but too many cables. So for example, in the picture that you can, there are like 6 equipment that you can see, and the equipment 1 and the equipment 3 is connected through the red wire. For example, the equipment 2 and the equipment 3 is connected through one blue cable. So every equipment is actually connected separately with using different kind of wires. So this is a distributed one, because all these connections is like distributed to specifically to each equipment. But what is the centralized data bus? So there is only one data bus that you have in your system. So there is only one line, one channel. And all the equipment is actually connected to that channel to give information and then get information through that channel. Instead of distributing and then dividing every connection separately, we are just centralizing every connection in the centralized data bus. So what is the advantages? It's like just a standardization, fast data transfer, easy and fast implementation, and an ease of error tracking. Because if you have like multiple wires that is connected between the different equipments, so it will be easy, harder for you to find a bug. Because if there is any problem, you need to follow the cable from which equipment is actually going to where, and then you need to understand if there's a failure in that part or if there's any failure on the other parts. So it will be harder to detect a bug. But in the centralized one, because every equipment is actually connected to the same line, so it will be easier to understand what is the failure. So in the aircraft systems, there are like generally 2 data buses are used. First one is the military standards 1553, and the second one is the orange 429. So we will just talk about it a little bit. We will not go into details. The first one is the military standard. As the name already suggests, it is a standard used in the military, which is developed in the US Air Force in 1973 for faster and easier data transfer between the systems. So you can also see like some of the military standard used in first one is the F-16 aircraft, and then they also use them some of the other versions in again F-16s or the Apache helicopters, those kind of. I mean, this is the standard used in the military. So let's not get into too much detail because it will be too much confusing. But what is important is like the what we are calling is like a half duplex system. So what is a half duplex system? So through one line, at the same time, only through one direction you can send data. So if one equipment is actually sending to the others a data, you cannot send the information back through the same channel. So this is what we call half duplex. But if the technique is like the full duplex, then you can also send in both ways the information. So then what we are doing is actually at one time, there is only one system is actually sending a data from one place to another. And this should be controlled by some guy. And this is why we have like a bus controller. So this is actually controlling all the bus. So it's actually sending signals to the equipments to tell them which equipments needs to send data to where. So at one time, so it's actually saying that at one time, only one equipment can send through that bus only one information. So there shouldn't be any information that is sent back to the same equipment. So let's go over those. I mean, these are kind of like the details of the system, so you shouldn't be actually going too much. So what is the orange? The second data bus is actually, this is the communication protocol used for the civil aviation, not for the military aviation, because what they came up is like using military aviation standards in the civil aviation is kind of expensive. So they just come up with a much more simpler protocol to be used in the civil aviation. So what we say that in the military, there should be a controller. So what it's actually doing is the controller is actually controlling which equipment is actually sending the data. But over here, there is no controller. There is only one transmitter in the system. And this is the only one is actually sending information to the other ones. There could be some receivers, which is up to 20 receivers that can be connected to the system, but only there is one receiver is actually sending data. I mean, the transmitter is actually sending data. No, the other receiver is actually trying to send data. So this is much more easier and much more less complex design when you compare to the military standard protocol. Because in the military standard, there could be a controller that is controlling the system. Again, we will not just go into details, but in the picture, as you can see, there is only one transmitter and there will be the receiver parts. I mean, you can just think the transmitter as like a subsystem, and then the receivers are like maybe the other subsystems or maybe the microcontroller in your design or in your architecture. But the transmitter part is the one who's actually sending signals to the other ones. So as we said, these are like the two data buses used generally in the aircraft. Military standard is used mostly in the military section, but the orange section is used in the civil aviation. So let's start talking about the avionics subsystems. So what are they? I mean, they are like the human-machine interfaces, which is like the display systems, communications, data entry control, flight control systems, because there is an interaction between the human and the machine. So the machines will be like the screens or the controlling parts, like maybe joysticks that you're controlling your aircraft or any other, or like again, screens or the keyboards that you're entering some information data to your systems. So this is why we are calling them like the human-machine interface, because there is an interaction between the human and the machines. The other subsystems will be like the air data inertial systems, the navigation, the communication and the surveillance systems, and the automation systems. First, we will talk about the air data and the inertia. So it is the information that is necessary for the flight crew to perform its flight safely. I mean, this is the most important data that a pilot needs during its actually flight. And we are just categorizing them under three main sections. First one is the altitude, second one is the airspeed, and the third one will be the air temperature. So in order to calculate the air data, the system requires three fundamental data. First one is like the static air pressure, second one is like the total air pressure, and third one is like the outside air temperature. So if you're using or if you have used a pitot tube, I mean, this is the information that actually pitot tube is actually providing to you. Static air pressure, the total air pressure, I mean, around your aircraft, and the outside air temperature. So with those informations, actually calculating a speed for your system. And these informations will be going to the air data computer to calculate your speed, your pressure, altitude, and the temperature that you are actually flying around the aircraft. So as we already said, this is like the pitot tubes that is actually getting the air pressure information, and then a temperature sensor that is used to understand the outside temperature around the aircraft. So these are some of the ADCs, air data systems used during some of the projects, also in TUSAŞ and also in other companies. But what is the importance of the data for the flight crew is with the calibrated speed information, the dynamic pressure information on the aircraft can be obtained. This information, the forces and the moments acting on the aircraft can be also calculated. So the pilots, when they are actually controlling the aircraft, trying to understand how the aircraft can actually behave, if there is any more forces that is coming from one side or on the wing or on the tail section. So it will try to do a maneuver according to those forces. So the controllability of the aircraft will be affected with that data. The altitude information is also important because for a safe flight, there are some actually aircraft crash because of the wrong altitude data information. Because if the pilot doesn't know if he's flying really near to the surface areas, it could be a sea, it could be a mountain or any landscape, so it doesn't get any information about the altitude, and it also doesn't get any vision from the outside world, so it cannot understand how it's actually flying. So then, and there are also some accidents that happened in the past. He doesn't get that information and then crash the aircraft. So this is really important information, data for the pilots to fly the aircraft with the safety. So again, I mean, also to the pilots and also for the subsystems, this is really important because the subsystem is also using these air data information to calculate some other informations and then show it to the pilot. I mean, the reasoning is the same because if you're getting any wrong data, then your calculation will be wrong, and then you will be showing wrong information to the pilots, which will affect the flight safety. So the first one will be talking about like the altitude systems. It will be calculated from the static air pressure, and then there are some basic standards atmospheric calculations, US atmospheric calculations according to the altitude levels. So if you are in the low altitudes, this is how you can actually calculate your altitude according to your static air pressure value. So in the formulation, the PS is like the static pressure in inch mercury, and the H is like the altitude in the feet. There's an inverse relationship between the altitude and the static pressure. So if you are gaining altitude, you're actually the static pressure that you're inside, that will be decreased. The reason is like that there will be less air on top of you, so there will be less air is actually pressurizing you. So that will be the reason that's actually decreasing in the static air pressure if you gain altitude. So there are two types of the altitude values. First one is like the barometric altitude. This is the altitude measured with the reference to the sea level. So whatever you're calculating for that barometric altitude will be your altitude according to the sea level. So after some of the aircrafts, after the aircraft lands at the airfield or wherever you're actually landing, the value taken from the barometric altitude will be the altitude of that airfield. So the second one will be the barometric corrected altitude. So this is the, for example, if you don't want to get an altitude value according to a sea level, but to the airfield's altitude level. So what you need to do is, through that barometric altitude level, you need to understand the barometric altitude of that airfield, and then you need to give that information to your system so that it can directly calculate your altitude according to the airfields, not to the sea level. So this will be your barometric corrected altitude. So the airspeeds, again, the most basic airspeeds velocity is calculated based on the difference between the total air pressure and the static air pressure. And this is the generic formalization of that one. And again, over here, the airspeeds that you are going to calculate will be knots, and PT and the PS will be the total air, the static air pressures. There are 5 types of airspeeds that we are using in the aircraft. First one is the indicated, second one is the calibrated, third one is the equivalent, fourth one is the true airspeeds, and fifth one will be the Mach number. Indicated airspeed will be the speed of the aircraft relative to the surrounding air mass. This is directly calculated using the static air pressure and the total air pressure that you already shown in the first formalization. When you wanted to use a calibrated airspeed, this is the airspeed obtained by making aircraft-specific adjustments to the ASI information. So you first calculate the indicated airspeed, then you calculate the calibrated airspeeds. And what are those specific adjustments will be like the pressure losses experienced according to the placement of the sensor. I mean, you're just putting your picotubes around your aircraft, mostly on the fuselage part. But if there is, I mean, you don't know exactly if those information is correct or not. So what you are just actually doing with those experiments that you conducted before the flight for your aircraft, you will try to understand the correctness of the information through every picotube that you're actually placing on your aircraft. So you're just doing that adjustment to understand the airspeed information. The third one will be the equivalent airspeeds. This is like a theoretical airspeed used by the aircraft designer, not by the pilots. The pilot doesn't use that airspeed to decide on any stuff. But this is the calibrated air velocity is obtained by adding the density and the compressibility data of the air that is surrounded by the aircraft. The fourth one will be the true airspeed. So what you are actually adding as the last information will be the temperature that is around the aircraft. So when you add that information also to your equivalent airspeed, you will come up with the true airspeed information. And the last one will be the Mach number. So this is the number obtained by dividing the true airspeed by the speed of sound. So the air temperature. So this is one of the 3 values that we need to calculate, need to sense on our aircraft through the sensors. There are like 2 kinds of air temperature. First one is like the static air temperature. The second one will be the total air temperature. A static air temperature will be the temperature around your aircraft. So it's not going to change. It's just like the air that has that temperature around you. But what is the total air temperature will be the when you're actually your aircraft is actually flying through the air. There are like some forces that's also acting on that air around your aircraft. So you're actually trying to heat also the all around the aircraft. So this will be the total air pressure, the temperature, not the pressure, the temperature that you need to calculate. So air data systems, as we would say, trying to get like three important information through its sensors. First one will be the static, the second one will be the total air pressures, and the third one will be the temperature. So all this information is actually processed in the ADC units to calculate all these velocity informations, all these again like temperature information for the pilots, and they will be shown to the pilots to actually fly the aircraft safely. This is again a schematic of an air data system. Like there are like two air data computers in your aircraft. So what we already told you, there shouldn't be in just only one subsystems or only one systems or one data channel in your aircraft. There should be always at least three systems, because if one of them is actually failed, the other one started to give you the right information. So this is again a schematic architecture that's showing like having like two air data computers in your system. So all of the two air data computers are actually getting two different sensory informations from different sensors, and then trying to calculate the same information for the pilots. Heading and situation information systems, what we call is like the AHRS, the altitude, attitude, and the heading reference systems. Like the air data system provides the necessary information for the flight crew to fly the aircraft safely. So again, we just categorize them under three sections. First one will be the attitude, the second one will be the acceleration, and the third one will be the heading, the magnetic heading. So in order to calculate the data, we need different kind of sensory systems, and that the system receives information from three different sensors. So first one will be the accelerometers, which will give you the acceleration through three different axes, which will be the X, Y, and Z axes. The gyroscope will be actually give you the spins according to the same axes, and the magnetometer is going to provide you the information how your heading is actually according to the real north. These are some of the AHR systems that's used in the TOSAGE project or any other of the projects around the world. So for the heading and situation information system, first one will be the situation. So how your aircraft is actually looking toward which direction. So this is the calculation of the state information of the aircraft by measuring the rotation around three axes. So how you are going to actually get that information is using the gyroscope, because the gyroscope is actually giving you how much your aircraft or whatever you are using is actually rotated around one axis. So if you are having like a gyroscope, you are getting the rotations around three axes, so which will give you the situation information about your aircraft. So in which directions actually it's rotated and in which directions actually looking. The acceleration information, I mean, if you know the attitude of your aircraft, so if you know where your aircraft is actually looking, so you also know the X, Y, Z axes of your aircraft. So what you need to know is how your aircraft is actually accelerating through those axes. So if you know those information, what you know is actually kind of like the speed of your aircraft. So in which direction you are actually having what kind of speeds, and then how you are actually in which direction you are going. So again, the calculation needs like three axes. So with an IMU sensor, you're actually going to get like three different acceleration information for like three different axes. Again, the heading information will give you how your aircraft is actually headed, in which direction is actually going according to your north, your true north. This is again a system that is providing heading and then the attitude information to your subsystems. So how is actually going to get through three different sensory informations like IME sensors, gyroscopic sensors, and the magnetometer sensor. It's going to get all these three information and then trying to calculate to you an attitude, velocity or acceleration, and then the heading information. So after calculating all these informations, what you need to do is you need to display them to your pilot. I mean, as I already told, the pilot could be on the ground for like UAV systems. There will be a ground control station, which all the information is actually provided to the pilot, or it could be a cockpit, and where your flight crew, your pilot, will be inside of your aircraft. And the flight information to the flight crew through the visual means the mission can be accomplished safely and successfully. And then for that information, you need to show some primary flight informations, navigation informations, engine data, airframe data, warning informations. I mean, the most important one will be the primary flight information, because if the pilot doesn't know those, it cannot fly the aircraft. The other informations are, again, navigation of course is important, but other information is kind of extra information for your pilots to have. So for the display systems, we are actually dividing them into three categories. First one will be the head-down displays, which will be the basic displays that we all shown in the aircraft. Head-up displays will be the more advanced display systems used in the also for the civil aviation and also for the military aviation. And the last one will be the helmet-mounted displays, which is mostly used in the military section and not used in the civil aviation. Head-down display will be the basic display that is shown information to the pilots. And also the old times, whatever you are seeing in the first picture on the right side, in the upper part, is like a head-down display. You are just showing information to the pilot that is coming from your subsystems. And the one in the downside is also a head-down display. Right now, you are just using MFT screens to give information. But the general purpose of all these screens and everything is the same. Just give the necessary flights and the aircraft information to the pilots to just fulfill their mission. Head-down displays, what we always say MFTs, multifunction displays, is a type of display where the multiple data can be shown to the pilot at the same time. So as what we've seen in the first picture over here in the upper side, every system like the altitude system, the speed system or the heading information has like showing all their information. But what the MFT's multifunction display is actually getting all these information and then showing them on one screen to the pilots. So there are like two types of those screens. First one is like the smart multifunctions. The other one is like the dumb multifunction displays without any data processing. So as the name suggests, the smart one is actually getting the data and then process it by themselves. They're just getting raw data, process the information, and then show the necessary information to the pilots on the screens. But for the dumb ones, there is no processing capability, so they just got the processed data and then show it on the screens to the pilots. So, and these are like the technologies that we have been used also in the old times and nowadays. First one will be the cathode displays, which are like the big screens, much more heavier. I mean, they just got heated more in the old times. Like these are like the televisions that we also used in our childhood and in the past times. And nowadays there is no any, I mean, usage in the aircraft and also in our daily life. So what they come up mostly is like the active matrix liquid crystal displays, like the LCDs. So also nowadays are in our homes or in another place, what we are using as like screen is like the LCDs. Also in the aircraft, most of the information is shown through the LCD screens. Uh, this could be like a future idea, although it mostly use MFT technology, but OLED screens can be also used. But right now it's too expensive, and then there's not like a common usage in the aviation. So what we have is like the primary flight display. We already talked a little bit about it before, like the basic T configuration. So what we are showing the file is like on the left side is the airspeed, right side is the altimeter, and in the middle with the heading and the status indicator we were showing as an information to the pilots. And in the MFTs, it will be the same that we already talked before. We will show you the same information to the pilots in the same manner. On the left side, it will be the speed, right side will be the altitude, and in the middle, the status and the heading information. And we are just going to divide it into two sections, the attitude direction indicator part and the horizontal situation indicator part. The first one will be the attitude in the direction indicator. Will just have like the air velocity, attitude, altitude, vertical speed, the direction, angle of the aircraft, which will be the upper part of your screen. I mean, there's an image on the right side, and the upper part will be actually showing you the attitude direction indicator. And on the below part will be the horizontal situation indicator, which will actually give you the compass display, approach information, and the navigation informations. So as we all talked, the upper part will be the ADI and the lower part will be the HSI. So the upper part's information will come from the air data, which will be the airspeed, the altitude, and the vertical speed information. And then the other information will come from the status data that we will talk. I mean, we just talk about the air data systems and then the HRSS systems. So these two systems are actually going to provide all this necessary information to be shown on the MFTs. I mean, let's not go into too much detail because this is like we already say that there are like some speed information on the left side of your MFT that's shown. On the right side, there will be the altitude band that show the altitude information. In the status indicator, this is like as like the basic T organization. It will be in the middle. There could be some directional indicators also, like the return rate indicator, vertical speed indicators, like the direction indicators that can be shown also on your screens. But again, this is like the general way of showing the information on the MFTs to the pilots. So after you are showing like primary flight informations data to the pilots, what we will talk that you can also show other information to the pilots. It could be like the navigation screens or the engine information screens. For example, on the right side, you're just seeing a radar information that is shown on the aircraft to the pilots. And on the right side, there are like some the engine informations that's shown to the pilots. Again, an engine indicator. I mean, these are, I mean, the screens that you can actually design according whatever information that you want to show the aircraft and the pilots. I mean, if you have the necessary information through your subsystems, so you can easily design those screens and then show whatever information you want to the pilots. So this is an inside of an F-35. So as you can see, there is only just screens. So there is not just like the buttons. I mean, of course, there are some buttons on the right and the left side, but the main part is just like the big two screens, MFT screens, and all of these information is actually flown to the pilots through those screens, and then I mean, you can just get whatever necessary information he needs for the aircraft to fly safely. So for the head-down displays, what we have is like the backup light indicators. So why we need it? Because if any of those our indicator main screen, if there's any malfunction or if there's any malfunction in the information that is coming to those screens, what the pilot is going to need is like a backup flight indicator. So I mean, this is like an information that needs to be shown to the pilots for the safety operations, and it will be like the basic flight parameters. These are like the primary flight parameters, which will be the status, the airspeed, and the altitude information that is shown. And it will be the same organization, like the T-shape organization, that is used also on the MFTs, and it will be the same on the backup flight indicators. But what is the difference is this backup flight indicators has, their information, whatever they are going to show is, that the information comes from different, sensory information. They are not going to come from the same information that is shown in the MFT sequence. MFT sequence is going to get their data from different sensors, different air data computers, status computers, data computers, but the backup flight indicator is going to get their data from different sensors and different air data computers. So that's the important part. So let's go back, go forward. Let's not go into too much details. On the head-down displays, there are like some warning panels. If there's any critical warnings or any failure in your aircraft, these are the panels that you show the information to the pilots. Of course, there are some master cautions and master warnings. If there's any caution, it means it's just showing to the pilot that there is a failure in one of your subsystems, but this is not just like a real main failure. So you need to be careful about it. But you need to also give information to the pilot. But if it is a warning, it means that there is a failure in one of the subsystems and which can affect the flight of your aircraft. So you need to show that information to the pilot in which subsystem there is any failure that's happening. Also, most important part is the fire part. If there is any fire in there, that definitely affect the flight safety. So you need to show that information to the pilot. So some of the, again, like the avionic architecture of warning panels from which subsystem is actually connected to the which warning indicator in your aircraft. We are also showing it as like a avionic architecture. So another one is like the engine indicators. Well, we already shown some of those. You can also give some engine information to the pilots just through the indicators. The information that you want to show could be different for different kind of motors. Some of them, for example, is like some level of temperature that needs to be actually worked on. If there are some levels that is just too much for the aircraft, you need to show it to the pilots to just work with the aircraft safely. So let's talk a little bit about the head-up displays. The first one we talked about, like the head-down display. So these are all the necessary information that's shown to the pilots through the MFT sequence. This is a head-up display, but what is the reason of having a head-up display is for the pilots, because for the head-down, the pilot needs to look to the screens to get the information. And then when it's actually looking to the screen, it's getting its contact with the visual contact with the real world around the aircraft. So what is the reason that we come up with a head-up display? I mean, when the pilot is actually looking through the window to the around area, it's like he can actually get the same information, same primary flight information through those screens. So it doesn't need to, lose its contact with the real world. So it can also get those information when it's actually looking through the window. So this is the reason they came up with the head-up displays for the safety of the flight operations. It will be like the same information that is shown on the primary flight displays. As you can see on the right screen, there is in that picture. On the left side, the airspeed information is actually shown. On the right side, the altitude information is shown. And in the middle side, like this is the status indicator is actually shown to the pilot. So it will be again like the basic T information. So whatever information you're showing will be the same manner to the pilot. So, but he's actually getting those information while he's actually looking through his window. These are different, some of the different pictures of the head-up displays. I mean, the ones that you're actually seeing over here is like for the civil aviation parts. So these are the head-up displays used in the civil aviation. But there are some also used in the military parts, but it mostly consists of like 3 units. Pilot display unit, the control unit, and the power unit. The pilot display unit is the ones that you're actually seeing over here, like the screens that you're showing the information. The control unit is like the pilot is actually controlling those informations. What kind of information he wants to see on the screens is actually controlling, and the power unit is actually the general unit that gives power to that head-up display. I mean, we will not go into the details of how those actually images actually shown on those mirrors and those screens. This is kind of a little bit too advanced for you. So we will just go through those. On the right side, what you are seeing is like a head-up display used in the military aircrafts. So on the bottom part will be the control unit. The pilot is actually controlling the information, and on the screen part is actually the information is shown to the pilot. So the last part will be the helmet integrated display. I mean, this is, as we said, the first part, the head-up display, is also used for the military, but it's mostly used in the civil aviation. But for the helmet integrated part is the reverse. It's mostly used in the military parts, not used in the civil aviation. What is the difference between the head-up display? Head-up display is just a screen that is locked. So if the pilot wants to have that information, he needs to look through that screen. But helmet integrated display is the same display that's shown in the head-up displays, but it is integrated to the helmet of the pilot. So the pilot is just, whenever he's just turn its head, it's actually also turning that screen, so they will always see those informations. So this is why they used in the military aircraft, the pilots, because needs to have a look around its surroundings all the time in the combat areas. So that's why it's just trying to get that information all the time, not just looking to one locked screen, but whenever it's actually turning its head, it's also, he will also have those information at the same time. So when you compare the head-up display and the head-mounted display, the head-up display can only display the flight data when looking in a specific direction, but the head-mounted display will always give you the data wherever direction you're actually looking. The head-mounted display definitely have a wider field of view, and it is a much more complicated system when you compare to the head-up display. When you're designing, of course, there should be some helmet design factors because this time the pilot is actually putting that helmet on top of its head. So the reason is it should be have like the features to protect the pilot's head also, not just to give information, but it should also protect the pilot's head in emergency situations. The systems providing oxygen to the pilot must be integrated. The necessary equipment for the pilot to communicate with the ground station and other aircraft should be in the helmet also. The last information that we're going to give is like the helmet integrated targeting, and it is like they're using the same helmet integrated display, but this is used to target any place or any aircrafts around the pilot's actually aircraft. So when it's actually looking one direction, it can try to get a target in that direction. So, I mean, in the, again, like the military aircraft, this is used because it will be easier for the pilot to just like to have all these maneuvers and everything inside of a combat area. So the other subsystem we will talk about will be the navigation systems. So what is navigation? In the aviation definition is the safe and the shortest flight paths through a flight will follow from the moment of takeoff to the moment of landing. I mean, the exact position of the airplane on the flight path must be continuously monitored through the references. And this is a definition of the civil aviation. I mean, when you're trying to go from one place to another, you need to have like a safe flight and you need to know exactly the location of your aircraft. Types of navigation, I mean, we have like 3 different types of navigation system. First one is the terrestrial radio navigation systems. It will be the information you get from the ground beacons. The second one will be the satellite navigation systems. In this time, your beacons will be on the space, like the GPS, and then you will get all those information through those CPS, space beacons. And then the last one will be the inertial navigation system. So you will not get any information from the outside, but all the information is actually calculated through the sensor system that is inside of your aircraft. So you will not get any information from outside, nor from the ground, nor from the space. So you will all calculate all the positional information through the inner sensor systems inside of the aircraft. The first one, as we already talked, like the terrestrial navigational systems, as we already said, there will be some beacons on the ground, and then you will try to communicate with those beacons, and then you will try to estimate your position according to those beacons. So this is how you can calculate the position of your aircraft. There are like 3 different kind of systems. First one will be the automatic direction finder. Second one is the very high frequency omni range. Third one will be the distance measurement equipment, and the fourth one will be the tactical air navigations. The automatic direction finder, this is one of the oldest radio navigation system used in the aircraft. The broadcast from a non-directional beacon towers on the ground is detected by the automatic direction finder on the aircraft and shows the bearing of the aircraft relative to that beacon. I mean, it will just show you what is the direction of your aircraft according to that ground beacon. So, of course, if you have just like one beaconal information, you cannot understand the location of your aircraft. So what you need is at least from two different beacons. You need to understand the bearing of your aircraft according to those beacons. So what you can do is actually you can just draw a line, because if you know the degree, that the bearing according to that beacon, you will just draw a line from that beacon to that location. And then if you have like 2 lines from 2 different locations, the connection point will be the location of your aircraft. So this is like the old system that you can use in the navigational systems in the aircraft. The ground stations broadcast at a low frequency, therefore the system does not work according to the line of sight principle. We will just talk about a little bit line of sight. So what is a line of sight? So if you have like one transmitter and one receiver in the radio communication, so what is the line of sight is these 2 transmitter and the receivers should need to just see each other. So if there is any device or if there is any landscape or anything that is behind, I mean, between them, not behind, between them, so these two devices cannot actually communicate with each other. So this is the principle of line of sight. So it should be in the line of its sight. But for the low frequencies, I mean, the working principle is not line of sight. So shouldn't be any sight between the transmitter and the receivers. So, I mean, for these ADF systems, these are actually working with the low frequencies. So they don't work with the line of sight principle. Very high frequency omnidirection range. So this is the receiver in the aircraft reads the broadcast of a VOR, I mean, a station on the ground, and calculates the angular position between the aircraft and the ground station with respect to the magnetic north. So this time, in the ADF, your aircraft actually know what is the location according to that beacon. But in the VOR, you also know the location according to a true north. So you can directly understand kind of the location of your aircraft with the VOR system. I mean, getting any information through a VOR. Of course, every station has like different frequency levels. So on the maps, they all show with different frequency levels. And if you want to connect to one of the VOR beacon, so you need to understand what is the frequency of that beacon, and then you need to connect to that beacon and get those images. Again, what we said, the line of sight principle, we talked about it. The VOR system actually works according to the line of sight principle. So if you want to connect to a VOR beacon on the ground, there should be a sight between your receiver and the beacon. So if your receiver actually cannot see that beacon's transmitter, you cannot get any information from that beacon. On the right side, for example, there is a simple actually image that's shown for you to understand that information. For example, on the right side, we have the VRB station, so it's actually transmitting a signal. But on the left part of that screen, there is an aircraft which only can get the VRA station's information, because it cannot get any information. There is no sight between the receiver of that aircraft and the transmitter of that VR station V. So as I said, if you don't have any sight between that beacon that you want to get any information, you cannot get it. So this is the principle of line of sight in the aircraft, and mostly in the higher frequencies, you are actually working with the line of sight principle. This is a VOR indicator, but we will not just go into details. So this is how the pilot actually understands its location according to the specific VOR beacons actually he is connected to. So we will not just go into details. It's just a little bit complicated. So the third one will be the DMEs, the measurement systems actually, these are. The aircraft sends, whatever in the VORs and the ADFs, you don't get any distance information. You will just get the positional information. So according to those beacons, where your aircraft is, you will just get as a position, but you don't get any distance measurements according to those beacons. But what is the DME is like the distance measurement equipment. So in that one, you're actually aircraft is going to send one signal to the DME beacon, and then that beacon is going to make a response to your signal. So according to those, you will try to understand the distance between your aircraft and then the DME station. So what is TACAN is? TACAN is you can just think it as like a military station where there is a VOR-like structure and a DME station at the same time. So if you just connect to a TACAN station, what you can get like the positional distance information from DME, and then the positional information from the VOR. So even if you just have like one taken on the ground, if you can connect and then get that information, you can understand the exact location of your aircraft. So this is how they show on the maps. So on the right sides that we have like the VOR or DME. If there is, I mean, if the station has like the VOR and the DME, it will just shown on the map with that figure. If it is just like VOR, it will be shown in the middle figure. And if it is like a VORTAC, which is like a TACAN that has a VOR station, it will be shown in the first figure on the maps. There is also radar altimeter, which gives you the altitude level of your aircraft according to the ground level that's actually passing. It could be the sea level, it could be any of the landscape, but wherever the aircraft is actually passing, if it is like a landscape, it will give you the altitude according to that landscape. So it's not going to directly calculate you a sea level altitude. So it will just directly calculate you altitude according to the whatever landscape that you are passing through. So again, it will just send a radio frequency signal, and then it's going to receive that signal back. And according to time passed during sending and receiving, it will just calculate the necessary altitude information. The satellite navigation systems. So this is like the GPS system that we already know, but of course GPS is not the only satellite navigation system that is used nowadays. We have also like the GLONASS from China, like from BeiDou from, GLONASS is from Russia, and the BeiDou is from the China. And Navig is from the Indian navigation system, but it's only open for the if you're inside of India. If you're outside of India, you cannot just connect to the satellites of Navig. And the Galileo is the European Union's navigational system, but it's not on online right now, so you cannot directly just connect the Galileo system. It's not ready. But most of our phones and every stuff that we are using as like GPS is actually using both GPS and the GLONASS system that's provided by the Russia. What is the difference between the satellite navigation system and the terrestrial navigation system is, as we alluded, in the first one, all the beacons that you are getting information is on the ground. But in the satellite navigation system, all those beacons will be in the space. So you will be talking to the beacons on the space, trying to get your positional information. So when we talk about like the GPS system, the American systems, there is like a three section. First one will be the space division. I mean, the design requires like 24 online satellites, but right now it is like 32 satellites are operational. And there is like a control section in US, in Colorado. There are like 5 control centers. I mean, one of them is like the main control station. It provides an accurate orbit and a time information. I mean, the importance of a central section, central controller is all these satellites is actually synchronized on a time, because if they are working on a different time zones or if in a different time sections, you cannot get necessary information through them, because GPS will be also the working principle of GPS will be the same like the radio navigation. So it will just try to send a signal from one place to another. So if it doesn't know the exact time that the signal sends from one location to the another, it cannot do all these calculations. So this is the reason why we have like a main controller on the ground to synchronize all this time information on those satellites. And the last section will be the user section. I mean, it includes all those receivers that you are using. It could be a aircraft, it could be your phone, it could be a car, anything that is just needs its position information to be calculated, and it will be the receiver side. So, I mean, the satellite part is going to send a signal, and the receiver part is going to receive that signal. How they are going to calculate those is actually in space. If you know the exact location of 3 points, and then if you trying to find a position of another point, the fourth point, and then if you know exactly the distance between these 3 points and that your 4 point, you can actually calculate, because what you're going to drive is 3 different equations, and you have like 3 different unknowns. And then if you have 3 different equations, you can easily solve it for your 3 unknowns. So it will be the exact location of your system in space. But for the GPS, what you need to have is like the fourth point. So for GPS to calculate your exact position, you need to have like connection between 4 different GPS beacons. The reason is because there is a time difference between your devices and the GPS beacons time. As we already said, all these beacons, it has like a time synchronization between them because of the main controller in the lens. But your device is not synchronized as a timeline between your devices and then the beacons. So what you need to have like, so in this case, you actually doesn't know like 3 unknowns. There is like 4 unknowns. There is a time error, time difference between your device and the beacon's times. So for that reason, you need to have at least 4 different equations. So this is the reason why you need like 4 different GPS beacon connections between your device and then to calculate the exact location of your device. The inertial navigation systems, what we taught for the satellite and the terrestrial, you need information from outside of your device or aircraft, whatever you're trying to define it as a position in the space. But for the inertial navigation system, you don't need any information from outside world. It will directly calculate it through the inertial measurements inside of your aircraft. I mean, calculating the exact position of the aircraft by calculating the inertial data of the aircraft. I mean, which will be autonomous. It will directly calculate it by itself. It doesn't need any information from outside. So it doesn't depend on any information from the outside world. I mean, at the heart of those inertial measurement system is like the IMU sensors, which are the inertial measurement units, which consists of like an accelerometer, gyroscope, and a magnetometer. According to those information, what you can calculate is like the altitude of your information, aircrafts, not information, your latitude and longitude, so which are the coordinates of your aircraft. You can just think it as like the XYZ position of your aircraft in the space, and your ground speed. But what is wrong with those systems? There is actually an error always in the system of the acceleration for the IMEs, you can say. I mean, the inertial systems operate with a certain margin of error by design, and every IME system has an error by itself according to their design. There is no IME systems without any error. So you can just think it as like when you start your aircraft to fly, from starting from the takeoff, there's an error in your system, and it will just going to grow by the time when you're flying. So it will start to give you like wrong information about the position and the speed of your aircraft. So this is the reason that you cannot always just depend on the inertial measurement unit data, because there will be always an error in your system. But what they are actually trying to do is trying to filter those data and trying to decrease the error inside of those inertial measurements. But how they are actually doing is doing it through the other positional data information, like satellite navigation information, terrestrial navigation information. So what they are actually doing in nowadays is not just use only one navigation information like satellite or terrestrial. You're just trying to combine all these three information to get a much more accurate positional and velocital information about your aircraft. So the part that we're going to talk about will be the communication and the surveillance systems, subsystems in the aircraft. After the navigational systems, the most important part is like the communication of those aircraft between the ground or any other aircraft that there's around. I mean, the sharing air and operational messages, ensuring air traffic control, collision prevention, acquiring knowledge about like the aircraft exterior and every those kind of information is actually get to the pilots through those communicational systems. So what we are using is actually again like the electromagnetic waves. Also for the navigational information, we were getting like the radio electromagnetic waves, radio waves we were using. All those information is actually sent from aircraft to those beacons and then getting back to those beacons actually through those electromagnetic waves. And all those communications also performed by those electromagnetic waves. So which are like the gamma rays, like the X-ray, ultraviolet, visible light, infrared, or the radio waves. And the radio waves is mostly used for like the communication, and we will see it. I mean, let's not get too much detail about the electromagnetic waves and everything. So let's try to understand why we are using them, and then in which areas we are actually using those. So what we have like for the radio frequencies, we have like the very low frequency, medium, high, very high, ultra high, super high, and extended high frequencies that we are actually using nowadays. But mostly our systems, also for like the navigational system, we already see we're using like the high frequencies, very high frequencies, or like low frequencies. They were using for like the ADF system. If you remember, they were using the low frequencies, so they were not working with the line of sight principle. High frequency communication with the frequencies corresponding to the high frequency range, which is the 3 megahertz to 30 megahertz range. High radio generally covers the range from, again, the same. The most important feature of high frequency radios is that they can be used in situations where the line of sight principle does not work. So if you are using the till the high frequency range, starting from the low frequency range, you don't need any line of sight. But if you start to work with the very high frequency range, then you need to have like a line of sight principle to just communicate between devices. I mean, we are not going into detail about what is the reason of having a line of sight principle and not. I mean, just know that till high frequency, starting from the low frequencies, you don't need any line of sight principle. You can just reach 1,000 kilometer range with those frequency levels communication. But if you start using very high frequencies, then you need to have like a line of sight principle. So we will just go over those. We will not talk about them. These are kind of, as I said, like some of the specific equipments and specific topics about those informations. Very high frequency. I mean, this is the assigned frequency range for the air traffic control. This is the range between 30 megahertz to 300 megahertz. Ground waves are used for communication. This is because of the line of sight principle again, so it's not just for you to concern about. So, I mean, as we said, in the lower frequencies, like the high frequency, you can have like a 1,000 kilometer range. But over here, you need to have like a line of sight principle. So that is The reason that you can only have like the communication around 200 kilometers possible, so it is much more decreased than the other lower frequency ranges. Ultra high will be the 300 megahertz to 3 gigahertz levels. It's a frequency band used in military applications. And encrypted and protected against jamming technologies are used in this frequency range. So one of the really important avionics subsystem is like the radio detection and ranging, which is actually start to be used in World War II. Is if you remember what we said for the World War II area in the beginning is like most of the subsystems of the avionics start to be used in those areas, and the radar system is one of them. And we are just dividing into two categories. The radar system is like the primary radar and the secondary radar. Primary radar is like the radar that we all know from the movies and everywhere, maybe from you already trying to understand those kind of information. This is the information that is if there is any surrounding aircraft or anything in the air, you will just try to understand through the primary radar. So what the primary radar is actually doing is trying to send a signal to one whatever thing that is in the air, and then receives it a signal that is bounced back from that thing. It could be a bird, it could be a aircraft, whatever it is. I mean, it's just trying to understand what is the location, what is the distance between your primary radar and then the thing that is inside, I mean, in the air. But it doesn't understand if it is an aircraft, if it is like a bird or anything else. So this is the reason they just come up with the secondary radar, because in the primary radar you don't understand if it is an enemy or if it is your friend, because it doesn't categorize those. It just tells you there is a thing that is in the air with a distance of this much. I mean, you cannot identify it. So this is the main not the failure, but this is like the negative part of the primary radar when you compare it to the secondary radars. As we all talk, the radar itself just sends the signal and then receives the signal that is bounced back from that thing on the air. So, what we call is like the ray bouncing of the object do not reflect back in a straight line, but this is like spread out. So, this is reduced the amount that, the transmitter part of the radar is actually receiving. And the beams that is returned to the radar section will be called as like the backscatter. Okay, so whatever you are actually receiving back will be the backscatter. And then when you are designing an aircraft, you are actually designing according to how much it's going to reflect beams. Because if you are designing a military aircraft, you want your aircraft to be not seen on the radar. So you don't want it to be like a round shape. So you're just trying to have like designs that can reflect the beams from the other direction, so it's not going to reflect back to the radar. But if you are in the civil aviation, you're just trying to design an aircraft that can be seen on the radar. You want it to be seen. So that's why all these aircraft in the civil aviation is much more round shaped. So these beams will be much more reflected back to the transmitter side. So as we already said, the secondary radar parts is there's also information about what the object is in the air. So there is like a transponder system, which is like a transmit to a response. So it is like the combination of two words. And the biggest difference of the secondary radar is like the presence of a transponder in your system. So this time you just send information to the aircraft, and then it will receive it and then send an information back to you. So this is why it's known as like the identification of friend or foe, because in this information you can understand this is an enemy or this is a friend. So there are like different modes in the secondary radar transponder, you can say. There's like the mode A mode where only the squawk codes of the rover is transmitted. Like there are like 4,096 different squawk codes that can be created with the mode A transponders. And mode C transponders is like the mode A, it will send the squawk codes and also the altitude information of the aircraft. But the mode S is like the mode select, which is, I mean, we will see in a minute that there will be sending much more information about the aircraft. So this is a model developed by the International Civil Aviation Organization. So it allows like a 24-bit address to be assigned to the aircraft, so that 16 million different addresses you can assign to the aircraft. Because for the SWAT codes, there could be only 4,096 different codes that you can assign. If it is more aircraft that is on the air at the same time, from that number, you cannot assign different numbers to the aircraft. So you cannot define them. You cannot just understand which aircraft is which one. But with Mode S, you can actually assign like more than 16 million different address numbers, so that there could be more than enough for your system to understand who is in the air right now. So when an aircraft reports a flight, it will always assign an individual code that cannot be changed during the flights. And this code makes it easier to recognize the aircraft at every point. So there are like two different information is provided through these transponders. First one will be the baseline surveillance variables. It defines the minimum criteria that any aircraft wishing to fly in European airspace must meet. So these are like the parameters that all the aircraft must meet, regardless of whether the aircraft is fixed wing, rotary, whatever it is. The first one will be the 24-bit aircraft address that we already said. There are like 60 million different addresses that you can create with the system, and this is assigned to an aircraft specifically. So there is no same number cannot be assigned to another aircraft at the same time. Second information will be the aircraft identification. This is like an 8-character flight code entered in the transponder by the flight crew via the control units. This, I mean, could be different from the 24-bit aircraft code address that is assigned through this system. It will be from the aviation company that's actually providing this information. The capability report, it is the message at the end of the interrogation at the ground station that the transponder has advanced or beginner level surveillance capability. So right now, this is like the baseline surveillance you're just sending. If you're only sending these 5 information, means that this is the beginner level surveillance capability. But if you're sending more information, which we'll see in a minute, it will be the advanced level of surveillance. This is the flight status. This shows whether the aircraft is on the ground or on the air. This is if it is on the ground, because the system doesn't try to get and send information to the aircraft because it's already on the ground, so it's not in the air. So it doesn't try to, I mean, just makes it easier to communicate with the other aircrafts. And this is the pressure altitude. This is the message transmitting the altitude of the sea level of the aircraft. So if you're sending these 5 information, these are like the baseline surveillance variables, and you can get those informations. And the first information will be from the transponder because it will automatically give an address value to the aircraft. The aircraft identification will be through the control panel. I mean, the flight crew is going to enter that identification number through the system. Capability report, again, will be transponder. It will be the baseline or the advanced one. Flight status will be coming from the landing gear. I mean, if the landing gear is open, it means that the aircraft is on the ground. If it is closed, it means that the aircraft is in the air. And the pressure altitude information will come from the ADCs, I mean, air data computers. The advanced surveillance variables, I mean, if an aircraft entering the European airspace had a maximum takeoff weight of more than 5,700 kilogram or a maximum cruising speed of more than 250 knots, then it must meet the criteria of the advanced surveillance variable. So it needs to give more information through their transponders. The first five will be the same as like the baseline, the basic ones. And then the other ones will be the magnetic direction, which is like the angle that the nose of the aircraft is actually according to magnetic north. The Mach number that we already calculated with our ADCs, Mach number of our aircrafts at that time. The indicated airspeeds is like one of the airspeeds that we already talked about. The vertical change is like how much the altitude is actually gaining or losing the aircraft is at that time. Roll angle is like the angle according to its roll axes. So how much the aircraft is at that time is actually rolled. Course angle change is like the rate of change in the angle of the aircraft ground speed vector with the geographical north. Root angle is like the angle of the aircraft ground speed vector with again the geographic north. Ground speed is the speed of the aircraft according to the ground, and the selected altitude is like the altitude data assigned to the waypoints that is the aircraft is going to go through according to its navigations. So there are some waypoints the aircraft needs to reach, and these are like the altitude levels that they are going to go in those waypoints. So this is an information needed for the control towers because they're going to know at which points the aircraft is going to reach which altitude level, so they're just going to prevent some collision on the air. And all those information is coming from different part of subsystems in our aircrafts. So again, like the first five will be already talked. The magnetic information will be coming from the GPS or INSs in the aircraft, like the Mach number, speed information, the vertical change. Again, like the vertical speed information comes from the ADCs. The roll angle can be also come from the INS systems or the GPS systems. The other four information can come from the INSs, GPSs, or the flight management systems that is in the aircraft. The last section will be the autopilot, so we will just go through them in a quick way, and then we will finish the course. The general purpose of the autopilot is to control the aircraft so that it can move on a set course without any control by the pilot. So what we are trying to do is we are just trying to minimize the task that is assigned to a pilot, because if it is like a long flight, the pilot is always trying to fly the aircraft by itself, looking all these informations, fly, having some decisions. It will be a really hard task. I mean, it was a really hard task in the past before. So with the autopilot systems, what we are trying to do is like trying to decrease the task that is assigned to those pilots. So the pilots can actually look to informations more instead of trying to control the aircraft. If there is any failure, if there is any situation that's the pilots directly control the aircraft, then the aircraft, of course, is going to give the control to the pilot. But instead of having all those controlling issues through the flights, I mean, most of the systems, like the autopilot system, is going to control the aircraft. Like what we already said, is the first autopilot flight is like the Lawrence Perry's flight in the history. At 1914, he flew over the people at the Paris air show by taking it from his glider source, and then showed all these people that it's gyroscopic system that is connected mechanically to its lever, unlike the glider lever. It's actually controlling the aircraft, and the aircraft is actually having like a cruise. He was cruising in the air without any disturbance from, and it was like a stable flight. So it was showing that the systems in the aircraft can be actually used to fly the aircraft instead of a pilot by itself. Of course, there are some like this is the history of the autopilots. Like in 1930s, the Sperry autopilots, the airplanes could fly for 3 hours without deviating from its route. Uh, in 1933, American fighter pilots Wiley Post-Perry completed the navigation of the world in 8 days, just using the autopilot systems. I mean, these are some of the historical parts of the how the autopilot is actually moved on. I mean, how they evolved through the history. What is important for the autopilot is like the instrument landing systems. I mean, they were developed together with the autopilot systems. I mean, the leading company is a UK-based company. I mean, the reason is because in UK there is like a rainy and foggy weather. I mean, most of the time there is a rain or foggy weather in the country, so that's why the companies trying to establish an instrument landing system that can make easier the landing for the aircraft. Because if it is too raining or there is like a foggy air, foggy weather, so it is harder for the pilots to do all this landing by itself. So these instrument landing systems are going to help the pilots to land the aircraft. I mean, the important one is like developed in 1958 is like the blind landing experimental unit below. I mean, this system is like the basis of today's automatic landing systems. I mean, for an autopilot, there should be definitely a fly-by-wire. I mean, in the Lawrence Perry's aircraft, there wasn't any fly-by-wire. All the systems is controlled by mechanically, but nowadays there are too many systems in your aircraft, so there should be definitely a fly-by-wire ecosystem in the aircraft to control all these surfaces and everything inside of the aircraft. I mean, all of the mechanical systems is replaced by these electronic systems nowadays. So the flight control computer controls the control surfaces with electrical signals only and according with the incoming commands. So how we are actually doing it is there's like a control sticks, rudder pedals in the cockpit area. I mean, through those sticks, you're just trying to understand how much the pilot is going to give an input to your system. And you just sense it through those sticks. And then you create an electrical signal according to those stick movements and then send those to your control surfaces or your motors, wherever, what you're trying to do in the aircraft. And then they just, those subsystems actually trying to control the aircraft. I mean, the pilot is not mechanically controlling the aircraft anymore. It's just trying to tell the aircraft how much the aircraft is going to, for example, to pitch down. I mean, through that rudder, through the stick control, and then the rest is actually done by the electrical controls in the aircraft. So what is the advantage? Of course, increased aircraft performance, because if you try to control it by mechanical, it's really hard because there are too many big aircrafts. It's much more easier to control the aircraft by fly-by-wire system, so that's why it's increased aircraft performances, reduction in the aircraft weight. Why we say that? Because all these mechanical systems, as you used in the past times, actually get rid of from the aircraft. So, instead of having mechanical controls, we have much more like electrical controls in the aircraft. So all these systems has like less weight in the aircraft, so it's actually reduced the weight of the total aircraft. Control interfaces become much more simpler and more compact again. Instead of having the control mechanisms between the cockpit and the controller, the control surface, you just have like wire systems, data systems that is actually flown through those systems. So it's much more simpler. Automatic stabilization and carefree maneuvering and everything is like the advantage of the fly-by-wire systems. So we also have like fly-by-light systems, but what is the difference is like between the fly-by-wires is like the cabling. And then if the cabling inside your aircraft is made by fiber optic cables, then it means that you are actually using a fly-by-light uh, system instead of a fly-by-wire. And as I said, only the difference between the wiring. If the wiring is fiber optic, then your system is called fly-by-light. What is the advantage will be again the weight, because the fiber optic cables has like less weight than the normal cables that is used in the aircrafts. I mean, the control surfaces part, I'm not going to talk about. You're already familiar with those because you're like, you always have like courses about those control surfaces. So I will not just talk about those. So autopilot, so control part is like the autopilot's task is to ensure that the aircraft reaches the specified position using two control surfaces. So there's like two control loops. The outer loop is like the autopilot system calculates the changes that needs to be made on the control surfaces to reach the specified position and transfers them to the inner loop. And the inner loop is like controls the changes in the control surfaces with the values it receives from the outer loop. It is a faster response than the inner loop. So the outer loops actually calculates how much they need to change the control surfaces to reach a desired position. And the inner loop part is get those information as like an input and then try to use that information to control the control surfaces to the desired output values. These are like some of the schematics shown for the altitude control for the inner and the outer loops. So we will move on with those. So what is the functions of the autopilot? I mean, the protection of the bar calculated altitude. So if you give an altitude level to your autopilot system and then says that you're just going to hold it, so even if the aircraft somehow, because of some of the reasons, just decrease its altitude or increase its altitude, it will just try to level the aircraft at the same altitude level that you wanted to fly, maintaining the vertical speeds. So whatever speed information you give to the autopilot, it will just trying to continue to that speed information and then trying to not decrease, not increase, but say you the same speed information, achieving and maintaining a predetermined bar calculated altitude. So if you say that at one waypoint you wanted like a desired altitude level that you want to reach, the autopilot is going to try the aircraft to reach that altitude levels, achieving and maintaining predetermined head alignments, capturing and maintaining a predetermined radio route. So what the autopilot is actually doing, you just give a route to the autopilot system. You want your aircraft to follow those routes in your system. So autopilot is trying to follow those according to the flight envelope of your aircraft. So it also knows what is the limitation of your aircraft. So it doesn't try to go outside of that envelope and trying to use the limits of the aircraft, but it will just use, it will be inside of the limits of the aircraft and it will try to follow the route that you specified for the aircraft to do during its flights. So one of the, as we said, important stuff is like the instrument landing systems. Let's go through them really quickly because we already, as we said, we will just have like a 2-hour course. So we'll just try to finish as fast as possible from here to rest. So what is the instrument landing system is used for? When you're trying to land your aircraft in an air space, in the airfields. So there are some systems localized on those airfields for your aircraft to actually maintain its position when it's actually reaching to the landing position. So the first one is like the localizer part. Localizer part is actually tells you the inner part that is between the mid lane. so that the aircraft will be just have like the same manner of the localizer line. So it's not going to land any part that's outside of the mid lane of the airfield. So what is the glide scope is like the information for you to reach to those landing position, because if you are outside of the glide scope, so because this is an angle specified for your airfield, so if you are higher than your glide scope, then you need to actually decrease your altitude. If you're lower than your glide scope, it means that you're actually much more closer to the airfield area, so you need to actually increase your altitude levels. So with those information, automatically the aircraft's instrument landing system is trying to land your aircraft. And all these information, again, it will get some from some of the beacons that is on the ground in the airfield. And there are some markers. These are, as I told you, the beacons that is on the ground. Outer marker, middle marker, and the inner marker. The outer marker is like located 6 to 11 kilometers from the start of the runway. So the ground elevation is like 300 meters, and then the tone is like 400 megahertz. So you're just trying to get a signal from your receivers in your aircraft from your outer marker, so that it should be around. I mean, your aircraft should be around like a 300 meter altitude, and then you're just in the way that the start of a runway. So the middle marker is like 800 to 1,200 meters from the start of the runway. The height should be around like 60 meters, and the aircraft height should be 60 meters to have a safe landing on the runway. And the inner marker is like the broadcast received at the beginning of the runway. So after the start of the runway, there will be no marker. This will be the last marker of the system, and it is the last broadcast station received in the ILS system. The height is like 30 meters, and after that, you're not going to receive any signals, and you will just, the aircraft should land itself safely. This is like just like a shown graph of the middle and the outer beacons on the ground, how they're actually transmitting. But we also have like a CAT certification for the autopilots that is designed and divided into 3 categories: CAT 1, 2, 3. But the CAT 3 is also divided into 3 categories: CAT A, CAT 3A, CAT 3B, and CAT 3C. So what is actually CAT 1 is doing is just trying to get the aircraft till the outer marker by the autopilot, and then after the outer marker, it gives the control to the pilot. So the decision altitude, as you already see, is like the 31 meter. And after the outer marker, it gives the control to the pilot, and the pilot lands the aircraft by itself. But if your autopilot has like a CAT 2 certification, so what it does is like it just gets the aircraft till the middle marker. So it will just try to understand, give the control and everything to the pilot after the middle marker. But if you have like a CAT A, a CAT 3 certification, so it can actually land the aircraft by itself. But according to the ABCs, it will just give the control to the pilots in different sections. So for fully automatic landing for CAT 3A, it will just control passes to the pilot after the landing. But for the CAT 3B, after the landing, it will just start traveling on the runway and then start to give the control to the pilots. But for the CAT 3C, it should do all the taxi and then just park the aircraft. It will just fully automated. It will land the aircraft. It will just do the taxi and then park the aircraft. But there is no system right now that has like a CAT 3C certification. So there is no autopilot that is used after landing. It should just do the taxi and the parking of the aircraft. But CAT A and B certificate, 3A and B certification is there. So there are some autopilots that can actually land an aircraft by itself without giving any controlling before the landing. So this is like the Billy automatic landing systems. So we will not go into detail about those. Let's try to finish the course. So the last part will be like the flight management systems. So this is an assist the flight crew by reducing the task they need to perform the flight. So the reason is like the economical benefits. First one is optimizing the aircraft performance along the route and thus saving the fuel. The air traffic, increasing the air traffic density and 4D navigation. Uh, Precision navigation resources from the INS, from the GPS board or ILSs, processing power, easily accessible high-power processor capability, and the bus systems, fast data sharing between systems and the evolving bus stations. And what is the task is like the lateral and the vertical position control of the aircrafts, calculating optimum aircraft speed at each stage. I mean, you can just think it as like an autopilot section. I mean, because what we said for the autopilot is it try to follow a route that you actually given to the aircraft to follow. And what the flight management system is actually doing is in an economical way, it will just try to follow all those routes and it will try to calculate what is the possibly the most economical, I mean, the flight time in matter of the flight time. So we will just talk about those, but I mean the last important part is like the 4D flight management, because why this is important is like the 3D is for the position and 1D is for the time, and the time is also really important for the flights of the, especially for the civil aviation, because there are too many aircraft that is on the air at the same time, and every company is also depending on the aircraft to reach their final destination on the right time. So for the flight management is really important, and this is what the flight management system is actually doing. So it will try to calculate the minimized time that is to reach the destination point, and it will try to give the pilots and also the ground stations information on when the aircraft is going to reach that destination, so which is really important for the air traffic control. And today, with the closed loop for the flight control, 95% of the flights have only like 48 seconds of arrival deviation. I mean, this is not like, don't think about like the company is just giving you a time of when the aircraft reach the destination. This is not, this is about like calculating the aircraft by itself with its flight management system, with all these conditions like the fuel condition, all the route information, when it's going to arrive to the destination. But this is the important information for the aircraft, for the pilots, and also for the ground, I mean the ground stations for the air traffic control. So this is the end of our course. So as we always said, this is actually a really long course in our company, but I'll just try to give you like the real basic informations in 2 hours. So if you have any questions, we can just ask it right now. But if you don't have any questions, we will just finish the course.
Teşekkürler hocam. Teşekkürler hocam.
Tamamdır. Ben teşekkür ediyorum. Ömer. Sorusu olan yok diye anlıyorum şu an. O zaman thank you everyone for just following my course. If you also have any questions in the future, you can just contact me. You can ask your questions, no problem. You can just get my contact number or my email from Görkem Hoca. You can ask him, and then you can just ask your questions also in the future. Thank you for attending the course, following it. Have a nice day.
Teşekkürler hocam.